The first application of the integral is the motivation for the integral perhaps itself, and that is computing areas. If you've got a function, let's say the square root of x, say between 0 and 1, then to compute the area between the function and the x-axis, you simply wish to take the integral between 0 and 1 of the square root of x with respect to x. And of course here you're going to find an antiderivative of this. This is x to the 3 halves over 3 halves. And you evaluate it from 0 to 1. That's to say we take the value of 1, which is 1 over 3 halves. And we subtract the value at 0, with the result that we get 2/3 for the area. Now, the situation becomes a little bit more complicated if the function is not directly above the axis. For example, if we were to take a look at the function x squared minus 1 between 0 and 2. This is a parabola opening upward. Looks something like this, between 0 and 2. Now what's going to happen here is that the integral will count this area as negative and this area as positive. So if you want the entire area between the function and the x-axis on the interval between 0 and 2, then what you need to do is to take the integral from 0 to 1, this being the point where the function crosses the x-axis, the integral from 0 to 1 of x squared minus 1, and take the negative of this and add to that the integral from 1 to 2 of x squared plus 1 with respect to x. So that here you will get x cubed over 3 minus x evaluated from 0 to 1, the negative of this, plus x cubed over 3 minus x evaluated from 1 to 2. And this is going to be the negative of the value at 1 is 1/3 minus 1. The value at 0 is 0. Plus, here the value at 2 is 8 over 3 minus 2, minus the value at 1, which is 1 over 3 minus 1. Again, it's a good idea to use parentheses here so that you do not get the quantities wrong. Now, it's clear that this is minus 2/3, and if you just taken the integral from 0 to 1, you would have gotten minus 2/3. What we want is the negative of that, or it's 2/3, plus 8/3 minus 2 is 2/3. 1/3 minus 1 is minus 2/3, so that's another 2/3 for a total of 6/3 or 2. All right? And it's important then, if you're going to compute areas with respect to the x-axis and you want the total area, that you realize that the integral counts the area when the function is below the x-axis as negative and when it's above as positive. And so you have got to solve for when it's equal to 0, when it's positive, and when it's negative, and then make the appropriate integration. All right, now we want to look at a situation where the more general areas are concerned here. In particular here, if you've got two functions, f of x and g of x, say here's f of x and here's g of x, with f of x larger than or equal to g of x on the interval ab, then we can look at the area between the two of them. In order to do this, if we partition up the interval from a to b, then we can approximate the area with a little rectangle, and the height of that rectangle is going to be f of wi, if wi is the point chosen in the interval, xi minus 1 to xi, the height's going to be f of wi minus g of wi. The width of the interval is going to be delta xi. And if we wanted an approximation here, we want to sum this up, I equals 1 through n, over the partition. And if we wanted the approximation to get better, we want to take the limit as the norm of the partition approaches 0. And this should give us the area between the function f of x and the function g of x. All right. Now, whenever you've got a sum like this, summation, let's say sum f of wi delta xi, I equals 1 through n, and the limit, as the norm of the partition goes to 0, you automatically note that this is going to correspond to the integral over the interval that was partitioned of the function f of x with respect to x. Right? This is the basis for a lot of applications of the integral. You set up a sum, you take a quantity that you can partition up into little pieces and add up all the little pieces and get the quantity back. You then note that that's going to be an integral, and you then use the fundamental theorem of calculus, find an antiderivative for this function, and that's going to give you the value of the quantity that you wished in the first place. So that here, for example, the function that's here just before the delta xi is a function of wi, and so this is going to be equal to the integral from a to b of f of x minus g of x. This is f of wi right here, and so that corresponds then to f of x minus g of x. The integral of that with respect to x is going to give you the area between its two. This would have been more apparent if f of x and g of x were both larger than 0, because then you could take and visualize that you take the area under f of x and subtract from it the area underneath g of x. For example, if we wanted to know the area between y equals x and y equals x squared on the interval 0 to 1, it's clear that we could get that by taking the area underneath y equals x, that's to say the integral from 0 to 1 of x dx, and subtract from it the area underneath y equals x squared, the integral from 0 to 1 of x squared dx. Right? The formula here says, though, that in general, we can simply take the integral from 0 to 1 of x minus x squared, the top function minus the lower function with respect to x, and that will give you the integral, that will give you the area between the two functions. In this case, this is equal to x squared over 3 by this x cubed, x squared over 2 by this x cubed over 3, evaluated from 0 to 1, which is a half minus a third, or a 12th. In general, if f of x is not larger than g of x, then what you may need to do is to determine at what intervals f of x is larger than g of x. So that, for example, if f of x looked like this, and g of x like this, we were interested in the area between a and b of f of x, of the region between f of x and g of x, we would want this, this, and this. And here, if this was the function f, and this was g, on this interval, f is larger than g, so you'd integrate f minus g from a to whatever this point was. And then on this next interval, on the first interval, f is less than g, all right, so you'd integrate g minus f. On the next interval, f is larger than g, so you'd integrate f minus g. And on the third interval, g is larger than f, so you would integrate g minus f. And you'd take the sum on those three intervals, and that would give you the area between the graphs of the two functions. We now want to take a look at the application of the integral to volume, or an application to volume. You've got a general solid here. However, it may look something like this. And you know that it's located between A and B. Right? And you want to know the volume of this solid. You can compute this volume if you can figure out the cross-sectional area as a function of x. If we know at x here what the area of this is, A of x, then it's going to be possible to compute the volume of this solid. This is because in order to compute the volume, what you'd want to do is to partition the interval up between A and B. Right? For a particular interval in the partition from xi minus 1 to xi, right, you'd wish to choose a point wi, and you now look at what happens here if we look at the volume between xi minus 1 and xi. In this case, it's going to consist of two pieces here, and it's going to be approximately equal to the area, that's wi, times delta xi. Okay? So if we were to add up all of these A of wi, delta xi's, we would have approximately the volume of the solid. If we now take the limit, as the norm of the partition approaches 0, this should give us the actual value of the volume, providing, let's say, that the area varies continuously as you go across here and the solid is reasonably shaped. Right? Well, this corresponds to the integral from A to B of A of x with respect to x. So that in order to compute the volume of the solid, if you know the cross-sectional area between the limits of the solid, between A and B, all you need to do then is to take that area and integrate it between A and B with respect to x. This will get you the volume. We'll be looking at some applications of this. We now wish to look at the volume of a cone, but actually by a cone here is meant a general cone. That's to say, a circular cone looks something like this. But we're going to consider any area whatsoever here, and a point above the area, or on one side of the plane of the area, connected like so, and the resulting cone. The point does not have to be directly above the area. For example, something that looks like this with the point over here would qualify. That's to say, you take up an area A and consider all of the line segments that connect a point of A to a point outside of the plane of A, and this results in a cone. A particular example would be, for example, a pyramid, which is a cone that looks something like this. We want to get a formula for the volume of anything that is formed in this fashion. Right? For that purpose, we want to consider this to have height h. And actually what we're going to do is put an axis here and make this equal to 0. Right? Then what we want to do is we want to find the cross-sectional area at x, because according to the previous tape, if we can find the cross-sectional area at x, we will be able to find the volume by integrating that area with respect to x between 0 and h. So consider, first of all, a little square situated here, and its projection down here from this point is going to produce a larger square. Like so. Now, if this square has for its side at x, s of x, then by similar triangles, you need a few of them, s of x is to x as s, the side of the projected square down here, is to h. This side is to this side as x is to h. So that s of x is equal to sx over h. And so that s of x squared is going to be equal to s squared x squared over h Now this is what? This is the area of the square at x. And this is equal to the area of the square times x squared over h squared. Where this is the area of the square down here. Since that's true for squares, if we consider this region as being made up of a number of squares of various size and we add up all the areas, we find that the area of the region at x is equal to the area of the base here times x squared over h squared. We now have a formula for the area as a function of x. Now what we want to do is to compute the volume. We want to integrate from 0 to h. That's what would be partitioned here. On the area at x, that's to say ax squared over h squared with respect to x. And this now is equal to a over h squared times x cubed over 3 evaluated from 0 to h. And a derivative of x squared, x cubed over 3. So this is going to be equal to a h cubed over 3h squared, or 1/3 ah. So if the area is a and the height of the cone is h, then the volume is given by 1/3 the area of the base times the height. Right? This takes care of a number of situations that you perhaps already know. The area here is equal to 1/3 pi r squared h. That's to say it's the area of the base times the height. The area here is equal to 1/3 s squared h, the area of the base times the height. And the area in general, no matter what the shape of the cone is given by 1/3 the area of the base times the height. Okay, we now wish to consider a specific type of solid which is called a solid of revolution. This is the type of solid that you get by taking a particular area and revolving it around an axis and getting the resulting solid. We start out with the simplest case. You have a function f of x between a and b. And you wish to revolve it around the x-axis. The resulting solid is going to look something like this for this particular drawing here. If we wish now to know the volume of the solid, the way to do this, of course, is to partition up the interval, or simply to consider that if we consider a point x in here, we get a disk near x, and that the area of this disk is f of x squared times pi r squared. Right? So if we integrate this from a to b with respect to x, this is going to give us the volume of the solid. We're going to look at some variations on this, and what you want to keep in mind is the general principle. Rather than memorizing a bunch of formulas, because the formulas will tend to become confusing. Another way to have looked at this would be to say, let's take a small element of the partition here, and then we would get a small disk. If we chose a point wi in xi minus 1 to xi, and the volume of the small disk would be f of wi squared times pi times the thickness, delta xi. We would want to sum that up, I equals 1 through n, and take the limit as the norm of the partition goes to 0, and that's going to correspond to this integral, so that the volume is equal to integral from a to b of pi f of x squared dx. As a specific example, let's look at y equals x squared between 0 and 1. The area underneath the graph looks like so. We would rotate this around the x-axis, we would get a trumpet-shaped thing like this, and the resulting volume is going to be the integral from 0 to 1, what you'd partition right, or if you like, from one end of the solid to the other, of pi times f of x squared, that's x squared squared dx. So this is going to be equals to pi. This is x to the fourth, so an antiderivative is going to be x to the fifth over 5, evaluated from 0 to 1. And so this is going to be equals to pi over 5. The resulting volume is pi over 5, and that, of course, is based on the fact that the cube with sides 1 is to have a volume of 1. Well, now it's more complicated solids of revolution. They don't get to be too complicated, though. Let's suppose that we've got a function f of x, and it's larger than, let's say, a function g of x, and that's above the line y equals c on the interval AB. We wish to revolve this around this line. It's going to produce something that looks like so, with a hole in it, and like so on the outside. There's going to be a hole through the center here that's shaped something like this. We want to know the volume of the resulting solid exclusive of the hole. We can write the cross-sectional area as we go here between A and B. At a point X here, the area consists of a sort of a washer or annulus shape with outside radius here. Since f of x is larger than c, the outside radius is f of x minus c. So if we square that and multiply that by pi, that'll give us the area of the outer circle. And now if we subtract the area of the hole, the area of the hole is going to be pi times g of x minus c squared. And now to find the resulting area, we wish to integrate this from a to b with respect to x. That will give us the area. If you wish to revolve this around a line y equals d, which was above f of x, which was above g of x, then the result would be, again, something with a hole in the center. All right. Here, however, the outside radius is, since d is larger than g of x, the outside radius is going to be d minus g of x. If you now square that and multiply it by pi, that will give you the cross-sectional area of this large circle. And if you subtract from that d minus f of x, that's the inside radius, d minus f of x, and d minus g of x being the outside. Take the inside radius and square it and multiply by pi. And this is the area of the outside circle. That's the area of the inside circle. And if we integrate this from a to b with respect to x, then this integral will give you the volume of the resulting solid that's obtained by revolving this area A here about the line y equals d. So this is the volume about C, and this is the volume about D. Now there are some variations on this. One of them would consist of the following. If you had two functions and it was easier to describe them as functions of y, let's say between C and D, we had two functions, say g of y, the larger one, and h of y, the smaller one, and we wanted to revolve them around the line x equals a. Right? Well, then you could perform the same operation here, except you would be integrating with respect to y. That's to say, at a point y here, the resulting object would have an inside hole and an outside radius like so, resulting in an annulus or washer shape here. And here what do we have? For the outside radius, we have g of y minus a. So if that is squared and multiplied by pi, that'll give you the area of the outside circle. Subtract from that the area of the inside one, which is going to be pi times h of y minus a squared. H of y minus a is the inside radius, and so now this is the cross-sectional area. You want to integrate this from C to D with respect to y. And this would give you the volume here, revolving this around the line x equals a. Right? If we wanted to revolve it around a line x equals b, where b was larger than g of y, which was larger than h of y, then the outside radius would be b minus h of y, which since b is larger than h of y, so you'd take that and square it and multiply it by pi. The inside radius is going to be b minus g of y, so b minus g of y squared times pi, and you then want to integrate this from C to D again with respect to y, and this would give you the volume of this rotated about the line x equals b. Right? And clearly, if you had something that was more complicated than this, you could perhaps break it down into pieces and perform this type of operation here on each of the pieces. Okay. So let's take a look at a specific example here. Let's suppose that we had the two functions y equals x and y equals x squared. And if we wish to revolve them, let's say around the line y equals minus a half. Perhaps that's more like this, resulting in a solid here that would look like this. I wish to know the volume of the solid. Oh, this is y equals a half. So this is the line y equals a half. This is y equals x squared, and that's y equals x. Right. Well, then we're going between 0 and 1, and at a point x here, we're going to have an inside circle and an outside circle. And the radius of the outside circle is going to be x at x minus a half. So x minus a half, or x plus a half, is the radius of the outside circle. That squared times pi is the area of the outside circle. X squared minus a half is the inside circle. So this squared times pi is the area of the inside circle. It's the radius. And so what we want then to do with this is we're going to integrate this from 0 to 1 with respect to x. And this will then give you the volume of the solids. In general here we won't do these. They're not particularly difficult. Some of them are actually going to turn out to be difficult. I'm just going to set up the integrals at this point and for at further points in the lecture. So at any rate, here's the resulting volume. This is the volume about minus 1. If we wish to revolve this around the line y equals 2 instead, right, then we would get, at each point x, we would get a disk again, except now the radius of the outside disk is going to be 2 minus x squared. 2 minus the x squared. So this squared times pi is the area of the outside circle. The circle that's removed is going to have radius 2 minus x. So that squared times pi is the area of the inside circle. This is the cross-sectional area. If we now integrate this from 0 to 1 with respect to x, it's going to give the volume. Right. Similarly here, if we wanted to rotate in a different direction here, if we took the same region describing x as a function of y, here we have x equals y. Here we have x equals the square root of y. And now if we wanted to revolve this around the line x equals minus a half, we could do that, and we would end up with something that looks like so. The cross section would again be a washer type shape or annulus, and here we would again be going from y equals 0 to y equals 1. We'll be going from y equals 0 to y equals 1. The outside radius here is going to be the square root of y minus a half, or the square root of y plus a half. That squared times pi is going to be the area of the outside circle. Y minus a half, or y plus a half, is going to be the radius of the inside circle, so that squared times pi is going to be the area of the inside circle. This minus this is going to be the cross-sectional area. You would now want to integrate that from 0 to 1 with respect to y, and this would then give you the volume about minus a half, the third volume here. So this is the first volume, this is the second volume, the third volume. Right? Okay. This integral is going from 0 to 1, but that's from y equals 0, and sometimes that's written here from y equals 0 to y equals 1. If it's not written, it's always apparent from the dy. I want to look now at another method of computing volumes here using integrals, which is called the method of cylindrical shells. It's useful for the following situation and others. If you've got a function f of x between a and b, now look at the simplest case here. If we wanted to take this region and we wanted to compute the volume that you'd get if you rotated this about the y-axis. Well, if you rotated this about the y-axis, you end up with something that looks like this. Like so. Something more or less like this. Right. We wanted to know the volume of this resulting solid. The way to get at this is to go back to the notion of partition this interval and look at what happens here to a particular piece here. It gets revolved around here and forms a small shell. Like so. If this was xi minus 1 to xi, the interval was xi minus 1 to xi, and we chose a point wi in that interval, then we compute the volume of the shell as follows. It's the entire cylinder minus the inside cylinder. The entire cylinder has got a height f of wi, and so this times pi xi squared is going to be its volume. The area, pi xi, xi is the outside radius, times f of wi. Pi xi squared times f of wi is going to be the volume. And minus then f of wi times pi xi minus 1 squared. This is the volume of the inside, so the inside of the cylinder, the inside of the shell, the cylinder that makes up the removed part of the shell. This is the volume of the outside cylinder, and so this is the volume of the shell. Well, if we wanted to approximate the area, we would add this up, I equals 1 through n, and take the limit as the norm of the partition goes to 0. However, this does not go over immediately to an integral. We do not have something of the form summation f of wi delta xi and the limit. All right? We want to get something of that form. The way in which we do this is as follows. We factor the f of wi out and the pi, and we then have what's left is xi minus 1 squared, and that can be factored into xi plus xi minus 1 and xi minus xi minus 1. This is xi squared minus xi minus 1 squared when you multiply it out. Okay? This is delta xi. Okay? What's this? Well, it's really nothing. But let's divide by 2 here and multiply by 2 out here. And now let's choose for our points wi the midpoint between xi and xi minus 1. So if wi is equal to xi plus xi minus 1 over 2, then this becomes wi times f of wi times 2 pi. And we want to sum this up, just as here, and take the limit as the norm of the partition goes to 0. In each case, this is going to be equal to this. This is going to be equal to this. And now this corresponds to something of the form a function of wi, delta xi, the sum, and then the limit. And so that this is going to be equal to the integral from a to b, what was partitioned, 2 pi f of x dx, x f of x dx. Now that is a formula for computing the volume of a solid generated by revolving the area under a function between a and b above the x-axis around the y-axis. However, this is not one that you really wish to memorize. It is a formula, however, and you can get at this formula intuitively by thinking of this shell here as if we looked at this shell and we thought of cutting the shell and rolling it out. If we cut this shell here, let's say, and rolled it out, we would end up with something that looked approximately like this. Now you have to be careful with doing this because obviously you can't do it without distorting the shell slightly. However, what we need to know is that in the limit, the distortion in the shell does not make much difference. If we rolled this out here like so, the length we would end up with here would be 2 pi wi. The thickness would be delta xi, and the height would be f of wi. Right? So this would then correspond to 2 pi x f of x dx. If you think of this as delta x, f of x is this height, and 2 pi x is this right here that you get when you roll this out. Right? So that this is the volume of the piece approximately, and this does correspond exactly to what you would integrate here. So if you write the integral from a to b of 2 pi x f of x dx, thinking of this as a shell that could be rolled out like so, it will give you the right formula. And this will allow you to also get formulas when the situation is slightly more complicated than this. Okay, we want to look now at a slightly more complicated situation. Let's suppose that we've got on the interval a, b, we've got a function f of x and a function g of x. G of x might look something more like this, in effect. It doesn't have to be positive. And we wish to take the region between these two and rotate it about the line x equals c. And this is going to result in some sort of a cylindrical object here. And we wish now to know what's the volume of this when we rotate this about the line x equals c. That's perhaps right here. X equals c. What's the volume of the resulting solid? Right. Now, to do this by cylindrical shell method, we would want to partition the interval between A and B. We consider a small shell here, a small rectangle here. This is going to generate a small shell like so. And the height of the shell is going to be f of x minus g of x. If we think of it as rolling it out, we get f of x minus g of x for the height of the rolled out piece. We get 2 pi, the wi is the point in the interval, but we think of that as x, and so 2 pi x minus c. X minus c is the radius, 2 pi x minus c is the circumference of the little piece, and delta x, which eventually becomes dx under the integral. All right, so that here, if we now integrate this from a to b, this is going to give us the volume of the solid generated by revolving this around the line x equals c, where c is less than a. If, on the other hand, if we wanted to revolve it around x equals d, right, the same method would apply. F of x minus g of x would be the height of this small cylindrical piece. 2 pi d minus x. D is the larger number here. X is the value in the interval here. Originally it's wi, but in the integral it becomes x. D minus x is the radius. 2 pi d minus x is the circumference. So the circumference times the height times the thickness. And then if we integrate this from a to b, because that's what was partitioned, this will give us the second volume here. As a specific example, let's look at, again, y equals x and y equals x squared. And let's use the shell method on this, and let's revolve this around between 0 and 1, where the region is going to be. Let's revolve it around the line x equals 2, resulting in something that looks perhaps like this. Right. By the shell method, we consider a small piece like this. It results in a small shell. The height of the shell, the upper function is x. The lower function is x squared. So this is the height. Right. The radius, if this is x here, this is 2 over here. So 2 minus x is the radius. And if we multiply that by 2 pi, this is going to be the circumference. The thickness is dx. So if we integrate this from 0 to 2, that's what was partitioned. This will give us the volume of this solid of revolution. And here again, it's important to notice that you really do not want to memorize formulas for this. The formulas look slightly different depending upon the situation. What you want to be able to do is to work with this type of problem so that you can write your own formula. Okay, we now want to look at another application of the integral. That's to what's called arc length, or the length of the graph of a function between a and b. We have a function f of x, and I'll draw a nice looking function here between a and b. It's kind of clear if you lay a string along here that you'd need a particular length of string, and we'd like to know what that length might be. And to do that, we're going to partition the interval between A and B to compute it. And the general interval in the partition is going to be from xi minus 1 to xi, and we're going to eventually figure on picking a point wi between xi minus 1 and xi. We then wish to consider these 2 points on the graph. This is the point xi minus 1, f of xi minus 1. That's this point. This other point here is the point xi, f of xi. Okay? So if we approximated this with a little line segment connecting them, the length of the line segment would be the square root of f of xi minus f of xi minus 1 quantity squared plus xi minus xi minus 1 quantity squared. That would be the approximate length of this if this was a relatively smooth curve. And to get the entire length, approximately, we would want to sum this up I going from 1 through n. If we wanted more accuracy, we would want to take the limit as the norm of the partition goes to 0. But now this is not of the form summation f of wi delta xi and then a limit as the norm of the partition goes to 0. We'd like it to be, but it's not. So what we wish to do with this is to try and get it to be in that form. And in order to do that, what we do here is we multiply by delta xi, and then we divide underneath the square root here by delta xi. So this becomes over xi minus 1 squared, and this also over xi minus 1 squared underneath the square root here. Okay, now this is f of xi minus f of xi minus 1 over xi minus 1 all squared plus 1 square root, and then that's multiplied by delta xi, added up, I going from 1 through n, and the limit is taken as the norm of the partition goes to 0. Right? Now we're going to choose our point wi. By the mean value theorem, we're going to suppose that f is differentiable and moreover, we're going to also assume eventually that the derivative is a continuous function. So such a function is called continuously differentiable. We're going to assume that f is continuously differentiable. And so we're going to choose a point wi between xi minus 1 and xi so that this is the derivative at wi. This can be done by the mean value theorem. So that then this quantity right here is equal to square root f prime at wi squared plus 1 delta xi, sum I equals 1 through n, and the limit as the norm of the partition goes to 0. That's this quantity down here when we choose this point for the wi. Now what you need to know is that if you know that this function is integrable, then any point wi in between xi minus 1 and xi will do to compute the integral. Because this now is of this form, and so we get that this is equal to the integral from a to b square root f prime of x squared plus 1 dx. So that this is the formula here for the arc length between a and b, sometimes written like this, L between a and b. That's to say, in order to compute the arc length, you take the derivative of the function, you square it, you add 1, you take the square root, and integrate from a to b. Now, if the function was continuously differentiable, that means then that this derivative is continuous. Its square is continuous. When you add 1, you've got something which is continuous. And when you take the square root, you've got something which is continuous. So the resulting function underneath here would be integrable, and so consequently choosing the wi to be the point guaranteed by the mean value theorem doesn't lose anything in the event that the function is continuously differentiable. Actually, functions which are a little bit worse than continuously differentiable can also have their arc length computed by means of this formula. Now, there's a slight problem here, and as a consequence of this problem, I'm not going to do any examples. The problem consists of this. Frequently, when you take a function f of x, differentiate it, square that, add 1, take the square root, you end up with something which, while the formula is correct here, it's not easy to find an antiderivative of this. A couple of examples of functions where it is easy are x to the 2/3, or x to the 3/2, or a line, obviously, mx plus b, but you don't need the arc length formula to compute the length of a line. These are ones where it is easy. There are several others where it's easy. Frequently, however, when you get this result here, you end up having to go back to something like the partition to compute the interval here. So it's not generally easy to find the antiderivative of something of the form f prime of x squared plus 1 square root dx. All right, we now wish to consider the surface of a solid over evolution. In particular, let's look at the simple case here. Take the interval from a to b. We take a function f of x, which is greater than 0. We revolve it around the x-axis, and we end up with something that looks like this. We want to know how much surface area, how much area there is to the resulting surface. Okay, to do this, what we want to do is partition up the interval from a to b and look at a small piece here, and look what happens when this is revolved around. Well, what we get, if we consider the endpoints, is a small volume here that looks like something that belongs at the bottom of a cone. It looks like the base of a cone. Now, if you recall that the arc length formula says that the arc length is the integral from a to b of square root 1 plus f prime of x squared dx. Right? This element right here is a small element of length. And computing this length is like adding up all of these individual elements of length. Well, it turns out that the area at the bottom of this cone is approximately what you would get. Right? In fact, it's exactly what you'd get if you choose the correct point between xi minus 1 and xi. It's what you'd get if you considered as if this was this length right here revolved around the x-axis at this radius. That's to say, the approximate volume, the approximate area of the surface between xi minus 1 and xi, say, is going to be given by the quantity that eventually becomes under the integral. This is the quantity that represents a little bit of length. So this is the length. Right? And now, if this becomes exactly what you'd get is if you treated this as though you could rotate this like a cylinder. Right? If we had a cylinder here, the area here would be 2 pi r times h. If we treat this as if it were h and multiply by 2 pi r, r in this case is f of x. This is the circumference, and the circumference times the length, you could check, is what you'd get for the area of this cone. This is approximate now. but the integral from a to b will give you the exact surface area of this, providing, let's say, that f of x is differentiable and has a continuous derivative. Okay? This, again, is something that you want to know the idea behind. You want to remember the element of length, but you want to know the idea behind this method of computing the surface area. Because the idea works if we were to use something other than the x-axis, for example. If we wish to revolve around, if this was f of x here, we wish to revolve this around the line y equals c, right? And resulting in something that looks like this. Okay? We would partition here between a and b. Okay. A small area of length here would be, as before, square root of 1 plus f prime of x squared dx. But now the circumference is 2 pi f of x minus c. And so you want to integrate this from a to b. Right? If we wished to revolve it instead around y equals d, where d was larger than f of x, then we would get, again, square root of 1 plus f prime of x squared dx. Except now the radius would be d minus f of x. The circumference would be 2 pi times that, and you would integrate that from a to b with respect to x. So depending upon exactly what you're doing, you get something slightly different. Right? The same method works for revolving around a line which is vertical. We'll look at that next. Okay. Let's consider now the situation where you've got a function f of x and you wish to revolve it between a and b around, let's say, the line x equals c, resulting in an area like so. We wish to know the surface area of this resulting solid. Now this computes just one side of that surface area. If you want both sides, if this is a thin sheet, then you would want to multiply that by 2. Again, partitioning between a and b, you get, for a small piece of length here, square root of 1 plus f prime of x squared dx. That's going to get revolved just like as if it was a plain cylinder. And so that here now, the point wi is in this interval. It's eventually going to correspond to x in the integral. And so the radius here is going to be x minus c. And the circumference is going to be 2 pi times x minus c. If you integrate this then from a to b with respect to x here, then this will give you the surface area. Right? Likewise here, if we wanted to rotate around x equals d, we would have the same square root 1 plus f prime of x squared dx, except now here, d minus x would be the radius. We would multiply that by 2 pi and integrate that from a to b. And this would be the second surface area. Let's look at an example. Let's suppose that we wanted to rotate y equals x squared, again between 0 and 1 here for simplicity, about the line x equals 2. Right? Then what? Since y equals x squared, y prime is 2x. Right? And so an element of length is going to be the square root of 1 plus 2x squared dx. In fact, if we wanted to know the length of this curve here, we want to integrate this from 0 to 1, and this would be the length. This is not going to be a particularly easy integral to evaluate, but it can be done. If we want the surface area, then we take square root 1 plus 2x squared, quantity squared, dx. And now, if this is x here, think of it as being in the interval dx, then 2 minus x is the radius, and so 2 minus x times 2 pi is the circumference. We want to integrate that from 0 to 1, and this is going to give you the area. Now this, again, is not necessarily an easy integral to evaluate, but this is the way to set up the integral. So this is the surface area of this resulting solid of revolution, and it's just one side. If you want to paint the whole thing, for example, you need to know the area of both sides. All the considerations up to this point have been those of geometrical things and using the integral to compute some sort of geometrical quantity. We're now going to look at quantity from physics, and the quantity is work. And in the simplest situation, work is defined to be force times distance. The idea being something like this. If a person is pushing a lawnmower with a particular force here, that force has got two parts. One is the one that goes into the ground, and the other one is the one that goes forward. It's only the forward one that counts. So the lawnmower is pushed the distance d, then F times d, where it forces the force in the direction of the distance, gives you the work that's done. Similarly, if a person takes a weight W and lifts it up a distance d, by, for example, let's say walking a 100-pound weight up 20 feet, then the amount of work that's done is given by the weight times the distance. The weight is a force. So a 20-pound weight, if this were walked up 16 feet, the unit in the English system is foot-pounds, because this is feet times pounds, huh? Pounds times feet. We won't be too concerned about the units, but obviously you have to keep them consistent. Okay, in the simplest situation here, work is force times distance. In the more complicated situation, when you've got a product, in the more complicated situation, you end up with an integral. That's analogous to the following. In the simple situation here, area is height times width. Now, if the height varies between A and B, then in the more complicated situation, the area is, here it's height times width. In the more complicated situation, the area is the integral. In the simple situation, work is force times distance. If the force varies as the work's being done, or if the distance varies, or both, then in the more complicated situation, you're going to end up with an integral. And that's one of the reasons why the integral is applicable, and that's to say that it generalizes quantities that involve a product of two other quantities. Similarly, the derivative is a general notion of a quotient, and with that in mind, it's perhaps not hard to imagine that the one should be the inverse of the other. Okay. We want one further thing here before we do a simple example, and that's what's called Hooke's law. You take a spring and it's got a natural length L, and if you move that spring out a distance x, then the force at the point x here on the spring is proportionate to the distance x. Here's the natural length L here. I'm starting this at 0. So that the force, as this is sometimes said, is proportionate to the elongation. That's the basis for making scales. If you knew that, for example, it took 3 pounds to move it out to this point x, then it's going to take £1.5 pounds to move it halfway. It's going to take proportionate amounts to move at a proportionate distance. Right? If you know if you know, for example, that it takes 3 pounds here to move the thing out to 1 foot or 2 feet, then you can compute K, and it tells you what K is for the spring. It's 3/2 pounds per foot. All right. Now, if we know K, and let's assume for the moment that K for our particular spring is 3/2, then you can also compute how much work it takes to move the thing between a point x1 and a point x2. If it's situated at x1, how much work does it take to move it to x2? Well, the situation here is that the force varies as we move this across here. It gets larger as we get closer to x2. So if we partition the interval up here, then the force is approximately the same across each element in the partition, and it's going to be F of Wi, the force at Wi. The distance traveled is going to be delta xi, and to compute the work, we would want to add all the little bit pieces of work up, I equals 1 through n, and to get this exact, we would want to take the limit as the norm of the partition goes to 0. This, of course, is exactly what you want here. This corresponds to the integral from x1 to x2 of f of x with respect to x. And for our particular situation here, we know that f of x is kx. So this is the integral from x1 to x2 of kx dx. And now there's no difficulty evaluating this. In fact, it's what? Kx squared over 2 evaluated from x1 to x2. Right? Now, so that here, if you want to compute the work involved moving a spring from one place to another, you can do it using what's called Hooke's law. That F equals kx, find k, and then you can compute the work involved. This is just one example. This is not a particularly a formula that you wish to memorize, even though this formula clearly does hold in general. If you wish to move something and the force varies as a function of x, you wish to move from x1 to x2, then the integral from x1 to x2 of f will give you the work. We're going to look at some other variations on this, which are a little bit more complicated. Okay. If you lift a particular weight W, a particular distance d, then the work involved is equals to W, the weight times the distance. Imagine the following situation, though. Let's suppose that there was a 20-foot long chain hanging over the edge of a building here, and we wanted to lift the chain up. And the chain weighed 2 pounds per foot. Right? Well, now, we're not going to have to lift all the chain the same distance. The bottom part of the chain here is going to have to be lifted more than the top parts. So if we partition the interval here between 0 and 20, right? And we consider a little piece of chain here, delta xi if you want, then if Wi is a point in the interval between xi minus 1 and xi, this little piece of chain is going to have to be lifted up the distance Wi approximately. The weight of the chain is 2 times delta xi. So that's 2 delta xi is the weight. So the weight times the distance is going to give us the work. If we add all of this up, going from 1 through n, this should give us approximately the work involved. We take the limit as the norm of the partition goes to 0, and it should give us exactly the work involved. And this corresponds then to the integral of 2x dx, 2 Wi delta xi, from 0 to 20. which is going to be equal to 2x squared over 2. You evaluate from 0 to 20, which is going to be equal to 400. Okay? So this says that the amount of work involved in lifting this is going to be 400, and the units are going to be foot-pounds if this was in feet, and this was in the weight of the chain is in pounds. So 200 foot-pounds is the work involved in lifting this chain up. Now let's take a look at another situation. Let's suppose that we've got a drum, swimming pool if you want, full of water, and we wish to empty the pool by pumping the water up over the top. Let's suppose that this thing was 30 feet, has a 30-foot radius and a height of 10 feet, and the water that was inside was standard ordinary water with 62.4 pounds per cubic foot as its density. We want to know how much work is involved. Right? Well, different parts of the water are going to have to be lifted different distances. The bottom is going to have to be lifted the most, the top will just have to be lifted a little. So what we want to do is partition this, let's say putting a 0 here and a 10 down here. Right? It's really not that essential as to what, where one places the partition. Well, let's make the problem a little bit more complicated, and let's suppose that the water was only up to the 7-foot level, which means that if we did put this here, then we would want to go from 3 to 10 and partition this, because it's between 3 and 10 that the water would exist. Right? With each element in the partition here, we're going to get a little slab of water. If this is delta xi, and wi is in the interval between xi minus 1 and xi, then this little slab of water is going to have to be lifted the distance wi. So this is the distance. The weight of the water is going to be pi times 30 squared, pi r squared, times the thickness. This is going to be the volume of the water. So this is the volume. And now if we multiply this by the density, 62.4, then this together right here will be the weight of the water times the distance, right, is going to be the work involved. And if we add this up and take the limit as the partition gets small, the norm of the partition gets small, we will then have the total work involved, and this corresponds immediately to the integral 62.4 times pi times 30 squared x dx, and we want to integrate where we partitioned from 3 to 10. Right? Now, if we'd done this differently, if we put 0 down here, then and 7 here, let's say, and 10 up at the top here, then we would partition between 0 and 7. Right? And setting up the problem with this in mind, we would have what? That the distance, the small piece of water here would have to be lifted would be 10 minus x. This is the distance. Right? The volume of the water is going to be again pi times 30 squared dx. Go immediately here to the dx. It's pi times 30 squared delta x. So this is the volume. The density is 62.4. So this is the weight. The weight times the distance is the work involved. And we now want to integrate this with partition here now between 0 and 7. So we want to integrate this between 0 and 7. With respect to x. And this then should, of course, give you the same answer as that, since it's the same problem. Right? If you were to put the coordinate system on you in some other fashion, You each need to be careful that you integrate over the interval that you partitioned, that you compute the distances according to the coordinate system that you're dealing with, and you're all set. I want to do one last example here with respect to work. Let's imagine a more complicated situation. Let's imagine that we've got a circular tank, half full, and now it has a radius of 30 feet, let's say, and it's half full, and we wish to empty it by pumping the water up and out over the top. Right? Well, here, I think it's convenient to put a 0 here and 30 down here, let's say, and minus 30 up here. And partition then the interval between 0 and 30. And with an element in the partition, we're going to end up with a small slab here of water. This is delta xi is the thickness. Right? Here, however, the thing to note is that not only is the force varying, but the distances. That's to say, as you change through here, there are different weights that have to be lifted, and they also have to be lifted different distances. To determine those distances, we want to consider that this is x, right? And since this is 30 over here, right, the radius is going to be the square root of 30 squared minus x squared. It's going to be the radius of the circle at x. So pi times this squared is going to be the area, cross-sectional area at x, times dx, originally delta x, is going to give you the volume, so that this is the area, this is the radius here, right? This squared is the area, times dx is the volume, right? Times 62.4, the density, this is the density. So this is the amount of weight of the small slab. It has to be lifted from x to minus 30. So it's going to have to be lifted x minus the minus 30, or x plus 30. So this is the distance that it's lifted. The weight times the distance gives you the work. Now we want to add this up, cross the interval that was partitioned from 0 to 30. And that will then give you the total work. So here you can get the total work, for example, involved in emptying this above the top. If we wish to pump this up 10 feet more above the top, then we would have x minus 40, or x plus 40. We want to take a look now at the subject matter of liquid pressure. And basically the idea is something like this. This is a water level here. And let's suppose we've got some sort of a rectangular, parallelepiped box shape submerged under the water, with an area of its top like so. And if this is submerged to a distance h, height h for the top, and let's suppose that it has got, that the rectangle has a height d, then what happens is this. Above this object, there is a quantity of water. And if you compute the weight of that water, that's what's responsible for producing the force on top of the box. If the density of water, or the density of the liquid, for water it's 62.4 pounds per cubic foot. If that's rho, Greek letter rho, then the volume of the water above the box is given by h times a. So this is the volume. And the weight of this water, consequently, is rho times h times a. Right? The density times the depth times the area of the top. Density times depth. All right? And so that this then is what's responsible for the force due to this being submerged underwater. The force is rho HA. Now, the definition of a pressure is force per unit area. And since the pressure at every point here, since this is all submerged at the same depth, is going to be the same, this is going to be equal to rho times h. The density times the depth. Density times depth gives you the pressure. Now, at every point underneath this water here, this pressure is exerted, and it produces a force, for example, on the bottom of the box here, upward, and the force, the second force on the bottom of the box, is given by the pressure times the area. The pressure is the density, rho, times the depth, which in this case is b plus h, and the area is a. So this is the force on the bottom of the box. And you can see that it's more than the force on the top. The difference between these two, if this one is F1, F1 is rho h a, and the difference between these two, F2 minus F1, is equals to rho d a, which is this right here, d times a, is the volume of the box. So this is rho times the volume. Right? And now, consequently, a box which is like this, which is submerged underwater, is not going to weigh as much if we were to attach it to a scale as it would in the atmosphere. In fact, the amount of weight that's going to be lost is rho times v, which is to say that is the amount of water that this box displaces. And this, of course, is Archimedes' principle, that namely that the loss of weight of an object in water is equal to the weight of the water displaced, or the loss of weight of an object in a liquid is equal to the weight of the liquid displaced. Okay, now this is for the simple case here, where you're dealing with a surface which is flat and horizontal and submerged all at a particular depth h. Suppose we were looking at, instead, let's say a rectangle which was submerged with width w, and let's suppose that the top of the rectangle was submerged at h1 and the bottom at h2. So this is h2 to here, h1 to here. Right? And now we're presuming that this rectangle is submerged vertically. Well, consequently, what's going to happen with this is that at different depths, there's going to be different pressure on this. If we partition the interval between h1 and h2 and look at the element of the partition, then everything along this little rectangular element here is going to be approximately at the same depth. If this is 0 up here at h1 and h2, and this is x, and we think of it as being in the interval dx, then what? W dx, the width times dx, is going to be the area. Right? And it's going to be the area of this little strip. And the pressure on this is going to be rho, the density, times the depth. Density times depth gives you pressure. And pressure times area gives you the force on the little piece. All right. Now what we want to do is we want to sum all this up between h1 and h2, and this is going to correspond eventually then to taking the integral from h1 to h2 rho x w dx. Okay, now this is still a fairly simple situation. Let's imagine that we've got a more complicated one. Let's suppose that we've got y equals x squared here, and this parabola between 0 and 2, or between minus 2 and 2, represents, let's say, the face of a dam. The dam is 6 feet under here. This is solid up here. And so that this is at 6 feet. All right. And each of these is to represent 1 foot here. And so let's suppose that we want to know the total force on this area here due to the liquid. Well, here we're going to want to partition the interval from 0 to 4, like so. And for a little element in the partition, the width of the dam varies. In fact, what? If we consider this as a function of y, or as a function of x perhaps, let's make this the positive x-axis, then what? This side right here is x equals the square root of y, and this side of the dam is x equals minus the square root of y. And so that the width here at a particular value y, I guess we're using this as a y-axis now, right? For a particular value y is going to be 2 times the square root of y. This is the width. Right? dy is, that's the width of this piece. dy is the thickness. So width times height. Right? This is going to give you the area. And now the pressure is going to be the density. 62.4 times the depth. The depth of this piece here, y is in this interval. The depth is 6 minus y. Right? So this is the density times the depth, which gives you the pressure. The pressure times the area is the force on the little piece. Right? And now we want to sum this up over the interval we partitioned, namely from 0 to 4. And this integral then should give you the total force on this area shaped like a parabola, top of a parabola, due to the liquid, the water. Okay? In general, if you've got a more complicated region here, or if the region is at a slant, it's the quantity of area which is exposed that determines the area. Right? It's not just the area that you view, but it's the quantity of area that's exposed. But consequently, an object which has more area exposed is going to have more force on it. And this is part of the reason why diving bells, for example, are made in the shape of a sphere, because a sphere exposes the least amount of area. Here's then how to compute the force due to liquid pressure. All right, we now want to take a look at the subject matter of moments. Let's look at a simple situation first of all. Now, since this is not a physics lab, we're not going to be able to prove this, but but this is sort of common experience here. If you've got a teeter-totter, right, and there's a weight W1 here at a distance D1 from the balancing point, and another weight W2 here at a distance D2 from the balancing point, from the center of the teeter-totter, then this whole system will balance when W1 D1 is equal to W2 D2. And there are a couple of ways of justifying that, but it's perhaps just easiest to take this as a fact. That's to say, if a heavy weight is put out here and a less weight is put closer, it's not going to balance. If a smaller weight is put, let's say, for example, if this is 50 pounds or 150 pounds at 4 feet, that will balance with someone weighing 75 pounds at 2 feet. I think it's common experience that if the person who weighs less sits up closer, that you can get the teeter-totter to balance. And it's going to happen precisely when W1 D1 is W2 D2. Right? I guess we can just refer to the fact that a person should check this with physical experiments to see that it's the case. Or you can also think through more reasons why this might be the case. At any rate, now let's look at a more complicated case. Let's suppose that we've got a lot of weights. W1, W2, W3, up through, let's say, Wn. Right? Located on some sort of a board here. And we want to see what happens here if we place a balancing point here, which is called a fulcrum, at a point X. And let's suppose that these weights are located at X1, X2, X3, up through Xn. All right? Where perhaps 0 is over here. Right? Then what you can do is compute what's called the moment of these weights about the point X. That's to say, we compute W1 times X1 minus X. And of course, this will be negative because X1 is to the left of X. And we add to that W2 times X2 minus X all the way up through Wn times Xn minus X. In short, we add up the quantities Wi times Xi minus X. And this is defined to be the moment about X. When this quantity is equal to 0, this will balance. You can see that that's the case over here. If we thought of this as being X, and then this is a distance, positive distance D2 from X, and this is a negative distance, when W1 D1, well, negative, plus W2 D2, where here current D1 is negative, was 0, you can get this balancing. So that when this is equal to 0, right, then we have the whole situation in balance here. The moments to the right here, the ones where the weight is positioned to the right of X, add up to the same moments for the weights positioned to the left of X. This is taken into account by the fact that we're looking at Xi minus X. It's negative to the left of X, and it's positive to the right of X. All right. At the point X where this balances, that point X is called the center of gravity, or the centroid. Right? And let's look at what happens here if we set this equal to 0. Well, in order for this to be equal to 0, we must have the sum of the Wi Xi equals to the sum of the Wix. Well, the sum of the Wix, we can take the X out of the sum and write this as the sum of the Wi. So at the point where this balances X bar, we will have this happening right here. That's to say we can solve this for x bar very easily. X bar is going to be equal to the sum of the wi xi, and this is I going from 1 through n, divided by the sum of the wi. This can either be done with weights or with masses, because of course mass is a constant multiple of weight, as long as you're talking about it at the surface of the Earth. All right. Well, what is the sum of the wixi? Well, that is the moment about 0. If we were to place the fulcrum here at 0, then the sum of the wixi would be the moment about 0. The sum of the wi is the total weight. So this is sometimes written as the moment about 0 divided by the total weight, or total mass. Okay, now that's the situation for a simple case where you've got a finite number of weights here on a line, and you wish to compute where this is going to balance. The more complicated case is going to involve integrals. In particular, let's suppose that we've got a rod here going from 0 to L, rod of length L, and let's suppose that it has got a variable density rho of x in weight, let's say, per unit length. Right? So that, and we now wish to know where this is going to balance, or sometimes you would simply wish to know what the moment that's produced by this about the point 0. Okay. To determine what's happening here, what we want to do is to partition this interval up. Right? And now, if dx is one of the elements in the partition here, it's xi, well, it's going to correspond in the integrals to delta xi, huh? Then, what? This little piece here, we can treat as if it were a single weight, and we would get that rho of x, the density, in weight per unit length, times the length, is going to give you the mass of the little piece. If we were to compute the moment about 0, we then want to multiply this by x. So this is the distance to 0. The directed distance, in fact, because if this was negative, then this would be a negative distance. And so this right here, that is the moment. So the density times the length is going to give you the weight. The moment is going to be the weight times the distance. Right? And now, if we want to know the total moment about 0, we want to sum this up from 0 to L. So this is the moment about 0. The total mass, you're going to want to divide this by the total mass, and that's going to be the integral from 0 to L, rho of x dx. Right? Each little piece has got weight, rho of x dx. We want to add that up from 0 to L to get the total weight. And so that then this gives us the quantity x bar right here. X bar is the moment about 0 divided by the total mass. Now, in particular, for example, if rho of x was equal to x squared and L was equal to 4, then this would say that the density of this is increasing as you proceed from 0 to 4, and given by x squared, and then the quantity x bar would be equal to the integral from 0 to 4, x rho of x dx. Rho of x was x squared, so this is going to be x cubed, divided by the total mass, which is going to be integral from 0 to 4 of x squared dx. Rho of x dx. And now this is going to be what? This is going to be x to the 4th over 4 from 0 to 4. So it's going to be 4 to the 4th over 4. I'm sorry, x to the 4th over 4 x cubed over 3, so this is going to be 4 cubed over 3. And so we're going to get 4 times 3/4, or 3, which says that this rod here going from 0 to L, if this is the density, is going to balance at the point 3. That makes some sense, of course, because the weight gets heavier as you get larger values of x, and this then is going to balance at 3. The situation gets to be more complicated. If we take a look at objects in the plane, we want to find out where their center of gravity is, at what point they will balance, or three-dimensional objects. We'll take a look at those shortly. One thing that does happen here, though, is this, that if you are computing the moment on about a particular point, you can take some of these weights together and treat them as if they all bore down on their center of gravity. So if we were to take these weights right here, we could treat them as if they were one total weight acting at this might be a second weight, acting at its center of gravity. Right? We could take a different quantity of weights and treat them as if they were a weight, a first weight here, let's say WA and WB, and as if they all bore down on their center of gravity, x bar A. And you could, if you then compute the moment using these two, or a finite number of them, you will get the correct result. That's to say, you can treat the weights as if they were, from the standpoint of computing moments, as if they all existed at their center of gravity. All right, now we want to look at centers of gravity for regions in the plane. And let's consider our original situation here where we had a rod with variable density, rho of x. Well, it may be that that really wasn't a rod at all. It may be that what that was the area under a function f of x laying down its side, and that it was f of x that contributed to the fact that the density was variable. F of x between A and B, for example, here. Right. Then, what? If this had a constant density here, rho, in weight per unit area, right, we would want to make the same type of calculations. That's to say, we would like to find out where x bar is here so that this balances. And the way to do that, of course, is to partition up the interval AB. Right? And if we take a particular element of the partition here and look at a small piece, we can treat the small piece as if its weight was exactly centered at the center here, and consequently as if it were pushing downward right here. And the density of this small piece is rho. The height is f of x, actually f of wi, but it's going to be f of x when we get to the integral. So this is the height. The width is dx, so that the height times the width is the area, times the density is going to give you the weight, right? And then times x is going to be the moment of that small piece about the origin. And now we want to sum that up from A to B to get the moment about the origin. Actually, in this case, the moment about x equals 0 is the way this is written, or the moment about the y-axis. M sub y, or moment about x equals 0. We want to divide this by the total mass. And then this will give us, when we do that, it will give us x bar, the center of gravity, as far as the x-axis is concerned, where we should balance this like so. And so the total mass of this is going to be the integral from A to B, rho f of x dx. Right? F of x is height times width is area times density is weight. And so if we add up all the little weights, we're going to get the total weight. And so x bar then is given by x rho f of x dx. Right? Now, as we go along here, we're going to get some formulas, and these are not the type that you want to memorize, particularly though you want to understand the principle involved. Now, this particular area here, all right, would balance if we put a fulcrum here underneath here like so. But we could also imagine if we laid it over this way here, right, and close it in weightless plastic if you want, and put a fulcrum underneath here like this, and we would want to know then, all right, where would it balance as far as the y-axis is concerned? That's to say, what would y bar be? If we put those two together, if this was x bar here, and that was y bar there, then where those 2 points meet, if you, which figure underneath there, if you like, the entire area will balance. It can't possibly tilt either this way or this way or that, and so consequently it can't tilt any which way whatsoever. Now that takes considerable more thought, but it's sort of experiential that you know that you can find a point underneath there where the thing will essentially balance. All right, let's take a look at our same region here. Here's f of x. Looks like this between A and B. And now let's partition the interval up so that this is length dx here, and there's a small rectangle. And now recall that we can treat the entire weight as if it were centered at the center of this rectangle. Right? Because this is a uniform weight, the center of the rectangle is going to be the centroid for the rectangle, and we can treat the entire weight of this as if it were centered there. So if we do that then, and we now compute the moment about the x-axis, all right, which is the moment about y equals 0, right? What? The weight here is f of x dx times rho. This is the area. That's the weight per unit area. So this is the weight. Right? The distance to the x-axis, right, is going to be f of x over 2. Right? And so that this is the moment. So this is the distance together. This is the moment. Distance times weight is the moment. And we want to add this up from A to B. So this is going to be the moment. If we were to put a fulcrum at the x-axis, it's going to be the total moment of this. And now if we divide this by the total mass, this should give us y bar. The total mass is the integral from A to B rho f of x dx, just as it was before. So we can compute y bar here by taking the moment about the x-axis and dividing it by the total mass. Okay, let's take a look at a specific example. Let's suppose that we're looking at the region between y equals x squared. All right. Well, here's 0 and here's 1. And y equals x. Right. And let's suppose we wish to find the centroid or center of gravity of this region. And we're assuming that it's going to be given a uniform density rho. Right. Well, let's partition the interval up here. And if this is dx, then this is slightly more complicated than before. But the fact of the matter is here we've got a little rectangle, and it is situated at x. So the distance to 0 is x. Its height is, if we think of this as f of x and g of x, a smaller function, it's f of x minus g of x. X minus x squared is the height of this. Dx is the thickness of the little piece, and so that this is the area of the piece. Now if we multiply this by rho, this is going to give us the weight of the piece. This is the distance to 0, and so we want to integrate that from 0 to 1 across the interval that was partitioned. So this is the moment about the y-axis. We divide this by the total weight, since we're doing this in weight, so total mass if we were doing it in mass. The total weight is going to be the integral from 0 to 1, rho x minus x squared dx. X is the top function, x squared is the bottom, so this is the height, this is the thickness of the little piece. So this is the area of the piece, this is the weight of the little piece, and so this is the weight of the total. Now, a thing that you can note here is that in general, if you've got a constant density, the density is going to cancel out of the picture here. And so that it doesn't matter, the center of the x coordinate, for example, x bar, is not going to depend on the density. If you make this twice as heavy, it's still going to have the same center of gravity. And so consequently, the center of gravity, or centroid, is really a mathematical object when you're dealing with something of constant weight. That's to say, you can think of this as not involving anything physical other than the geometry of the thing. All right? And what is this going to equal now? This is what? The integral from 0 to 1 of x squared minus x cubed divided by the integral from 0 to 1 of x minus x squared. Right? Which is going to be x cubed over 3 minus x to the 4th over 4, evaluated from 0 to 1, divided by x squared over 2 minus x cubed over 3, evaluated from 0 to 1. So this is going to be a third minus a fourth, or a 12th, divided by a half minus a third, which is a sixth. Or a half. A coincidence. X bar, in this case here, is 1/2. Okay. Well, let's take a look at the y bar. If we were to try and balance this. Now we could, since this is simple enough here, we could either compute this by partitioning this way, or we could do it by partitioning this way and treating everything as if it were at the center of the rectangle. Let's do the latter, because it illustrates a slightly different principle here, the principle we talked about before. Well, let's look at the moment of this about the x-axis. Right? Well, here again, x minus x squared is the height. Dx is the thickness. So this is the area of the little piece. If we multiply this by rho, we'll get the weight. Density times the area is going to give us the weight. And now we can treat this as if it were situated at the midpoint here. That midpoint is at the point x plus x squared over 2. The average of its two values. And now we want, so that this is the distance, and so that this altogether is the moment of the little piece. This altogether like so, and we want to sum that up from 0 to 1. We want to divide by the total mass, which we already figured out was a sixth. Well, a sixth row. The rows, again, we're going to cancel. Right? And now here we've got x plus x squared times x minus x squared, so this is going to be equal to 1/2 from the 2/2 here, integral from 0 to 1, x squared minus x to the fourth dx divided by a sixth. This is going to give us x bar. This is mx over m, I'm sorry, not x bar, y bar. Or y bar. Right? And so let's compute this here out of curiosity at least. A sixth divided into a half is going to be 3. And then we're going to have x cubed over 3 minus x to the fifth over 5, evaluated from 0 to 1, which is going to be equals to a third minus a fifth times 3. Right, which is going to be equals to so many 15ths. I'll divide the 3 into the 15th, getting 5 here. It's going to be 5 15ths minus 3 15ths, or 2 15ths times 3, or 2 fifths. So that 2 fifths is the y coordinate here. And then the two coordinates together is the centroid. The centroid is at 1/2 2 fifths. X bar, y bar. If you position a pin there at 1/2 2 fifths, this whole area should balance like so. Right? Or likewise, if you tie a string through here, it will balance, no matter what direction up is. Right? If you tie a string here, you can put this in any position whatsoever, and it will balance. Okay. So here we have then x bar and y bar for this particular region.